This weekend.
What?
47 meters down, they couldn't come up fast enough because you get the nitrogen gas or something in your brain or something like that, bubbles. And
Yeah, great, yeah. And I showed you a video on this a while ago, but I'm not going to show the video again. I'll just explain it. I'm glad some of you know what I'm talking about. So, okay, here you are down here. All right, this is the ocean floor. This is the surface.
Why am I laying on the ocean?
Okay, because you're looking at sea urchins. So now, if you want to come up, you have to come up slowly. That's what we're talking about. Why? Why? If you're up here, okay, you're fine. If you're here, you're fine. But if you're down here, you have to go slow. I don't know all the details, but if you're not that far below the surface, you can just shoot right back up. But if you're low, you have to go like, I don't know, like a meter a minute.
Decompression break.
You have to go slowly. So what's going on? Yeah, what's going on with the gases in your? Hey, morning.
You don't want to know what's going on with the gases.
Hey, I got nothing for you yet. Sorry.
Oh no, no big. Bye.
What's going on with the gases in your blood, in your body?
Pressure.
They're compressed, just like when I push the syringe in or put the top on. All the gases are getting dissolved in your body, more so than up here when we're walking around. So more of the nitrogen and carbon dioxide, there's more gases dissolved in your blood down here because there's a greater pressure. Increased pressure, more solubility in your blood. So if you shoot up, think of it this way. It's like shaking that bottle and then taking the top off. What's going to happen? All the gases are going to come flying out. Well, if all the gases come flying out of your body, that means they start exploding in your body.
So your
you
body
die.
It doesn't actually happen.
Yes, it does.
You explode?
The gas comes out of solution very quickly. You have tiny blood vessels and capillaries that can burst. And if you get the gas in your brain, you have gas expanding in your brain. You can imagine that's not a good thing, right? Because everything's very compact in certain small spaces in your body. So if you rise too fast, the gases come out of solution like the bubbles coming out of a soda, and you don't want that. You want them to do it slowly so you can normalize back on the surface. So this Henry's Law is exactly the problem with deep sea diving. And you can only stay down here for a certain amount of time. Because if you increase the pressure too long and increase solubility, you have too much nitrogen in your blood. You have too much gas dissolved that's not supposed to be. When you're walking around on land or on the surface of the water, you have an equilibrium, like a balance in your body. Certain amounts dissolved. Again, I'm not an expert, I just kind of know the general concept. So it's a really good example of this in real life, that you have to go real slow to kind of slowly decrease that pressure because the gases will slowly come out of your blood, the nitrogen in particular. Yeah. So anyways, that's Henry's Law. I'm going to draw a picture. You're going to draw it to help understand this a little bit better. We'll go to table G and relate this to table G a little bit because there's one more thing I want to talk about, and then we're going to learn about colligative properties. I'm going to show you that weird video again, the singing music video there, and then I'll show you a demo in the back, and then you'll have homework. All right, so picture time. Here we go. I'm going to let you guys, this is like an interactive picture. Okay, so I'm not going to try and draw soda bottles. I'm just going to draw this. All right, yeah, draw this. All right, so these two containers are supposed to be about the same size. You have a liquid down here, and then you have gas up here. So down here is a solution. We'll just say CO2AQ. So we have CO2AQ in the bottom. So again, think of like seltzer water or soda, whatever makes sense. All right, and then you have air up here, right? So you have air up here. You might have some CO2 gas. CO2 gas. All right, now here's the interactive part. I'm going to give you the pressure above the solution. In this one, it's 2 atm. In this one, it's like this room, 1 atm. Now, if CO2 is equal to just one dot, if you're trying to take everything in that I'm showing you and talking about here, you guys should be able to put the dots in the solution, but it has to make sense. Like the picture should look different but there should be like a ratio there. Why? Because the pressure in here is twice as great. So twice the pressure, half the pressure. So if you don't want to screw up your notes, I suppose you can wait. If you have a pencil, give it a shot. But at least maybe try and think about, all right, how many dots am I putting in here? How many dots am I putting in here? And everyone could draw this differently and still get it right. I'm going to stop talking and let you think about it for a minute. And then we'll have someone come up and show us how to do it. So I think on the Regents they would say draw at least 5 particles, something like that. They like to do that so you know kids just put one dot in. It's like hard to kind of show what that means. Almost everybody for you. I thought you wrote CO3 instead of CO2. Yeah, I just wanted to make sure. So Solomon and Amanda and Zeke gave it a shot. Any of you
I have it in my mind.
3 want to do? Yeah, I'm sure some of you probably have it in your mind. Who wants to go up and draw what they have? I like what all 3 of you have. They'll do one. All right. Tell them thanks. You can do the other. Just because she's, got a knee issue. So she's going to have to do hers based on yours, I suppose. Right, Sal? Oh, let's see. Let's hope they did it right, huh? 1, 2, 3, 4, 5. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 10. Good job. 10 there, 5 there. Everybody go ahead and do that, except I think you had 4 and 8, or one of you did, right? Yeah. So Amanda had 4 here and 8 here. 10 and 5. You could have 20 and 10. You could have 30 and 15. You could have 2 and 4. I wanted more than that. So at least 5 here, and then you have 10 here. Why? Right. Twice the pressure, twice the solubility. Think of it that way. So if 1 ATM, think of pressure as like pushing, that's the syringe, pushing down. Right? 1 ATM is pushing down. We can even put, let's say we put maybe like 1, 2, 3, 4, 5 arrows pushing down. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. You don't necessarily have to do that, you can just watch. But twice the pressure pushing down on the liquid, the solution, these CO2 not only can't get out, but actually more of this CO2 is getting pushed in. Here, it's the same exact concept, but lesser extent. The 1 ATM doesn't quite push as much CO2 into the solution, but that's the concept. Pressure pushing down doesn't allow CO2 to come out. How do you get the CO2 to come out? Well, put a hole in the top. Put a hole in the top. Or take the top off the soda, and then it starts to leak. You want to build the pressure up again? Just cover it. Or seal it, I mean. Put the top back on. Eventually, initially it'll start, initially it'll continue to evaporate. That's a terrible word, sorry. Leave solution. But it will build up again, and once that 2 ATMs reached again, then it stops. That's called the equilibrium pressure. You don't need to know really all that terminology. Just understand, once the pressure builds on top, no longer will this leave the solution. So this, it's already getting pretty firm. When we first grabbed this, it was probably a little bit harder than it is now. So I know the pressure in here is back to where it was before I opened it when this is really firm. because eventually this pressure will be reached. I take the top off, it all leaves again, I put the top on, it'll build up again. Once it builds up, it's going to keep that CO2 down. So if this was an airtight seal, this would never go flat because this pressure would stay constant and these would never be able to get out. Is this making some sense, I hope? So that's one thing you can do to keep more gas dissolved. With soda, seltzer water, just keep the top on, right? Keep the pressure above high. You want high pressure, and that forces it down. Gases go from high pressure to low pressure. Okay, so now go to table G. What's the other thing we can do to keep this even more carbonated than just simply keeping the top on? Go to table G. This is the last thing with this concept, then we're going to move on.
What was your question? What did you just say?
Go to table G. What else can we do, right? So let's use table G, but think real life. Okay, I have soda, I have seltzer water. I drink a little bit, I put the top on. I want to keep this carbonated as long as possible. Don't answer out loud, just think. So I keep the top on. What else can I do with this to keep it carbonated or fresher longer? Like what would you do in real life? Think about it that way. Now look at table G and how does that help us figure that out? All right, so again, think about soda. Besides keeping the top on, what else could you do to that bottle so that it stays fresher longer? Table G helps us. If you remember, there's some lines on there that are gases. Not many, but there's some. I think 4. 3? 1, 2, 3. 3. There's 3 gases on that chart. So Vanessa, I know I haven't given you guys a whole lot of time to think, so I'm talking constantly, but what's the other thing we can do besides keeping the top on? Good. How so? Very good. Yes. It's the opposite of what we've been talking about with solids. In the rock candy lab, how are we going to get more sugar to dissolve in the water?
Heat it.
You're going to heat it up. You're going to see. You're going to see the lab today. You're going to have there's a pie tin on a hot plate. There's going to be like a little bit of water. You're going to put a mountain of sugar in there. It's going to look like it's never going to dissolve. But as it gets hotter, it will dissolve. That's all the other lines on there. Solids dissolve better at higher temp. Most of them go up very sharply. Okay? Gases, so this, CO2, it's the opposite. You want to keep it cold. So the colder you keep this, the more stays dissolved, right? So we put it in the refrigerator, put it in basement, or the garage. People tend to keep things they want cold, right? One of those 3 places usually. So we want this to be, try and give you a Celsius degree, degree Celsius. Let's say, 10 degrees Celsius or 8 degrees. So we want this to be fairly cold, but why? So hopefully we get a lot of pressure forces the gas down. It stays in solution because you're kind of condensing the gas when you put a lot of pressure on it, so it stays down. What about temperature? What does that do?
It makes you drink cold soda. I don't know.
Right. I mean, we just like the taste maybe of things that are colder, but there's a scientific reason why. Why does the gas stay down here, stay in here if it's colder?
Does that have something to do with the? No, nothing.
Yes, the gas can't move very well. If it's moving slower, it can't really get out. Good. What else? What else? There's one other thing gases do when they get cold. They get closer together. That's the 2 concepts. And if they get closer together, they tend to have stronger forces, which mean they want to stay together. They don't want to expand and I keep wanting to say evaporate. I don't know why. That's horrible. They don't evaporate. They're already gas. It's gassier, gassier. The difference is dissolve. But if we can keep the gas condensed and not moving very fast, it'll stay in the solution. If you heat this up, what do all gases do when you heat them up? They expand. It's a hot air balloon, and then it rises. So if you heat these up, all the gas is going to leave. If I heat this up, eventually the top would blow off because all the gas would come out. It would try and expand and get out, move quick, a lot of pressure, and boom. So it's the opposite, right? So Henry's law focuses on pressure, but I'm also relating something we did talk about, just reviewing, that you want to keep it cold. Why? Because gases dissolve better when they're cold, and that's what table G shows us. All right. So I'm just gonna add that to our notes, put that underneath the picture. The other thing we can do here, also, if temperature is decreased, gases dissolve better. Also, if temperature is decreased, gas solubility increases. And I'm writing it kind of in fancy chemistry terms because that's what you might see on a test, right? They're not going to say, explain why if you decrease the temperature on soda, it doesn't go flat. Like that's like common way to say it. On a test, they're going to say this. Explain why when you decrease temperature, gas solubility increases. Why? Because gas particles move slower, they get closer together. Right, my penguin analogy. Haven't I used that with you all year? Goats, penguins. It's really, really cold out. You drive by a field with goats in it. If they're outside. What are they probably doing? Yeah, they huddle together. You ever see cows do that?
Yeah.
All animals do this naturally. If they're outside and it's really cold and there's a bunch of animals, they will get together. Why? Transfer heat, right. Body energy, right? Body heat. So gases do the exact same thing. Goats, penguins. You ever see any shows on penguins, like Planet Earth or whatever, in Antarctica? There's like hundreds of them huddled together. Anyone ever see this?
Yeah.
It's because it's negative 55 down there, right? So they huddle together and then they stand on top of their eggs. Not literally, but they're on top of them, keeping them warm. So the point is, what's that?
They waddle with them.
Yeah, yeah, and then it's interesting. You guys know how they take turns? Like the female's on the egg, the male go hunts, and then the male comes back, and then the female. It's just interesting how they do that. Not a lot of animals kind of take turns. It's like one of them stays with the babies, the other one does all the other stuff. They kind of alternate, which is interesting. It's kind of cool. But anyways, penguins, goats, cows, whatever makes sense. All right, that's the example. All right, one more thing for you here, just for
McCoy.
yeah.
Did you know that like cows know when it's about to rain? That's why they start to lay down. Like,
Yeah. I feel like that's an old wives' tale, but
every time I drive
I mean,
past
they
the cow field, they're
they
always
don't
laying down.
really know, but I mean, let's be honest. There's no way they really know. But yes,
But I
I've
mean,
heard that.
Isn't
that
like
they,
the temperature or something like weirded out or something like that?
It might have something to do with the pressure change.
Yeah, they
in
could probably
temperature,
feel it.
and
I don't
maybe
know.
they feel that. So
And
yeah,
they lay down.
there might be some truth to that. Yeah. Okay.
I just think it's cool.
All right. That is cool.
I mean, you think
What else can I do to this to keep it fresher longer?
not open it.
Shake it.
That's the opposite. It'll go flatter.
Keep it
faster.
still.
Keep it still. Something else I can physically do to this to keep it fresher longer before I put it back in the fridge. Think about the law.
Make sure it's tight.
Don't open it? All right, let's say open it. Okay. Drink some. I want to keep it fresh longer. What can I do?
Push the squeeze it,
Squeeze it.
and then put the top on. Maybe. I don't know. Imagine it went all over the place.
Almost did. I almost squeezed it too much. Okay. Now, if
That's a thing.
if the top is worth anything, if the top is good enough, this space will now stay this way. It won't slowly leak air. Why will this keep it fresher?
Because it has more. There's more. Some.
Well, okay, so she's on the right track.
There's more.
Well, so when I take the top off, it's, right, all the CO2 leaves, right? Then I put the top on. What did I say happens when I put the top back on? So initially, what happens?
Less space for CO2,
Right. So think of it this way: you have a container here, all right, and you drank some. You have all this space. So now the CO2 is going to leave and leave and leave until it fills this up. Once this is filled up, now the pressure will stop allowing more to escape. So if you take the exact same bottle, except this time you squeeze it, so now the level is up here, there's less space for the CO2 to escape. It fills up faster, pressure builds faster, less leaves the solution. I had a kid, see this isn't working very well, some tops work better. I had a student long time ago, first couple of years teaching, he was like, I don't believe it, no way, or whatever, so he like did it. He bought 2 bottles of Mountain Dew, and he like drank equal amounts. He put one back in the fridge, like just put the top on, and then he did this, he squeezed it, put the top on, and he left them in there for a week, and then he took them out, and then he poured them into glasses, and he said the one that he squeezed still had carbonation, and the one that he didn't really didn't have any, he was flat basically. So it does work. This is not working too well. You really need a good top for this to work, because it eventually looks like this is going to just go back to normal. But so that's actually, it's kind of silly to talk about, but it's Henry's law. This pressure builds up first, so higher pressure, lower pressure, so it's going to keep more dissolved. All right. I mean, this is kind of a pointless for real life because you shouldn't be drinking soda. But seltzer water, I suppose. You ever drink tonic?
Ew.
Like a gin and tonic, bro.
No, just the tonic.
Well, that's what all people drink. Like,
Yeah, tonic
it
water.
reminds me of like brand.
I've never had tonic. I've tasted like this. I've tasted this. I've tasted tonic. It's terrible.
gross.
Yeah, it's awful.
It literally tastes like you're drinking TV static.
Some people like it, but all right.
Yeah, like old people on cruises.
I guess, yeah.
Gin
What'd you say?
Gin and tonic.
He's like, no.
No, what is that? Sparkling water or something?
Yeah,
Cold
it's
Canadian.
All right, come on back here.
Like, looks like you said you need to go.
Frankie, can you, man, stop that, please?
Okay.